So if you have a data series, X, here's an example of a data series. The first thing you want to know about it is what's the average value. That will tell you what's going on. That's will tell you what's sort of typical or central for that data series. But the next thing that you want to know about a data series is how much variability is there? Is it mostly clustered around one value, or is there a lot of spread? We need a measurement of this. And today we're going to talk about the first measurement of this notion of variability in a data set, which is simply called variance. So there's a formula here, which we'll get to in a minute. But what I want to do is I want to look at this example of this data series, which is copied here. And I want to just calculate the variance of it by hand. Now, this is not something that we typically do by hand. Usually we plug this stuff into the computer and we ask the computer for the answer. But I don't want you to be too over-dependent on the computer. I want you to know in principle what's happening here. So I'm going to illustrate a calculation of the variance on this data set by hand. The first thing you'll notice here is a leftover calculation of the mean of this data set. This is not accidental. We need to calculate the mean first before we can calculate the variance. So if you don't yet know the mean of your data set, you have to calculate that first, and then using it, you can calculate the variance. The first thing that we have to do is we have to take every number in the data set, in this case there are 10 of them, and we need to subtract the mean from that number in order to produce basically a long list of distances, how far each data point is from the mean. So what I'm going to do here is I'm going to slowly go through this data set, and I'm going to subtract 6 from every value. Now, some of those values are going to be negative, of course, because some of these values here are less than the mean. But that's OK. I'll have some positive values and some negative values when I subtract 6 from every value. So here we go, subtracting 6 from everything. And there we go. Now, this column doesn't really have a name. I'm going to title this xi minus x bar. I'm going to try to convince you that that really is the right title for that column. Xi represents the data values individually, but sort of generically. X bar is our special symbol for the mean or average. And that's exactly what I've done. I've taken the data values and I've subtracted the average. And so xi minus x bar is the right title for this. The next thing that we're going to do to all of these values is we're going to square them all. Now, when we square them, I made a mistake here, excuse me. This should be 0. When we square them, every one of these values is going to be positive or 0 because the square of any number is positive or 0. So this one will be 0 when we square it. The rest of these values will be positive. So I'm just scanning this by eye to make sure I didn't make any more typos. Okay, so let's square all of these values. So -5 squared is positive 25. Then we get 4, 4, 9, 16, 9, 16, 9, and 16. So a good title for this column might be xi minus x bar quantity squared, because I have just squared the xi minus x bar column, so that's a natural title for that column. And I can see that I'm a little bit misaligned here, so I'm just going to adjust the alignment of this. Now, what do we do with all of these values? Now we add them all up. We're going to add up all of these values. So the simplest way to do this is to group them. So I've got 3 16s, and 3 16s makes 48. I've got 1, 2, 3 9s. That makes 27. I've got a couple of 4s. That makes 8. And then I've got 25 there. So 25 and 27 is 52, plus another 8 is 60, plus another 48 is 108. So that's the total of the squares of the individual data values subtract the mean. Okay, so this is a long and complicated process. You can start to see why we usually rely on the computer to do this. I still don't have the variance though. I need to take this value 108, and I'm going to divide it by 9. And you're probably wondering, where did he get that? This 9 is not the sample size. Actually, I have 10 data values in this sample. It's 1 less than the sample size. So however many data values there are, subtract 1 from that and divide by that. So it's like calculating an average when we add something up and we divide by how many there were, except we're not actually dividing by how many there were. There are 10 things added up on this. I mean, I've omitted the 0, but it was in that total. There are 10 things added up here, and I'm only dividing by 9. So that will give me, these numbers are rigged so that everything works out nicely. And that gives me a 12. And the 12 is the variance here. Now, the variance has a special symbol, just like the mean has a special symbol x bar, the variance has a special symbol that we always and consistently try to use to represent the variance. And so this is a calculation of the sample variance. We'll get to the difference later. The symbol is s squared, and that's not two symbols, or at least I don't want you to think of it as two symbols for now. The symbol for variance is s squared. Think of s squared as if it's just one letter. Don't think of it as the square of something called s that I haven't introduced yet. Just think of s squared like it's just one letter. And s squared is 12 in this instance. So this is how we calculate a variance by hand. This is not something that you should be doing every day. If you calculate a variance, you should usually use the computer to calculate a variance. But this is how, in principle, it works. Now, I want you to understand how to do this, and I may ask you to do this, but more importantly, I want you to understand this formula as a shorthand for everything that I've just illustrated here. I want you to see how you can decode this formula, and it really just instructs you to do exactly what you've seen me do. So let's take a close look at the formula. And when we're reading mathematical formulas here and trying to figure out what process they represent, we usually start from the inside and work our way out. So let's start with the inside of these parentheses, xi minus x bar. Xi, again, refers to one of the data points here, sort of generically, and x bar refers to the average of them. So xi minus x bar actually doesn't represent one computation. It represents 10 different computations because there are 10 different xi's in the data series. So this really represents 10 different computations, and they are the computations that I've illustrated here. Then that's in parentheses and that's squared. It has to be in parentheses because we're squaring the difference between two values. So that's in parentheses and squared, which means you should take those values and square them, which is exactly what we've illustrated here. Now, what else do we have in this formula? That explains how we sort of decode the meaning of this. What does this mean? Just as in the formula for the mean, a sigma means summation, and a sigma with a subscript I means add them all up for all the possible values of I. And so that basically instructs you to add them all up. That is what I performed right here. I mean, it doesn't really matter how I did it. I just took these values and added them up and got 108. So this sigma sub I means take all of these many values and add them up. It's interesting to see here, there are 10 things represented here, and there are 10 squares represented here. But this means add them all up. So this is really, once they get added, there's only one total which of the process of addition. And then I want to remind you here, just like we talked about in the context of the mean, n is a special symbol which conventionally means the sample size. And n minus 1, of course, well, what does that mean? 1 less than the sample size. So we take the sample size, we take away 1 from it for reasons which should be a little bit mysterious to you, but trust me, we take away 1 from it. We get n minus 1, which in our case was 9, and we multiply by 1 over that, which is the same as we divide by that, right? I could have written that as a big fraction. And then there's just one more part of this formula, s squared equals this. So this is basically the definition of the variance here. Technically, it's the sample variance, but I don't want to talk about the difference yet. So this is the definition of the variance, and it gives you a way of calculating s squared. So ideally, you can calculate the variance by hand from some given data. You can also read this formula and allow this formula to instruct you how to calculate the variance. So ideally, you don't even need this example. You can read the formula, understand its parts, and know what to do. But of course, we're still learning how to decode the formula. So it's a little early for that. So I want to emphasize here that this is not something that we often do by hand. If we're doing this in a spreadsheet, then we can just use the variance command. If we're doing this in Python or Colab, then we can just use the x.var function, which is illustrated in the notes. So this is a long and involved computation, and we usually rely on the computers for it.